let's talk about using the confidence interval for comparing systems. So we already saw few examples where we compared two systems and we said, well, they are really identical, even though the sample mean is 1 point something, but that confidence interval includes 0. So we are going to use that kind of thing to compare systems. But before we really use it, we have to understand a difference between what we are talking about. So there are two kinds of observations: paired observations and unpaired observations. Paired observations means we have one system on which we did something, and we have the second system on which we did exactly the same thing again. So the first number here corresponds to the first number here. Workload benchmark 1, benchmark A, or spec benchmark on the two systems. Then we took some other benchmark, and we did it on the second system, right? So these two numbers are related. Then we took the third benchmark, and we did it in both systems. Third number. This is called paired observation. Why? Because each observation on this side has a relationship to the corresponding observations on the other side, right? On the other hand, you have unpaired observations where you just ask 5 random people from one state and 5 random people from some other state. There is no relationship between the first person here and the first person there. So those are 5 random observations here and 5 random observations there. So you did 5 random things on one system and 5 random things on the second system. There is no relationship between the first observation and first, second and second, third and third. There is no relationship, right? So that would be unpaired observations. In both cases, you have, in the case of unpaired, you could have different number of observations as well. You could have 10 observations here and 5 observations there. In case of paired observations, you have exactly the same number. So if you have unpaired observations, then you need a little bit more theory that I haven't taught you. But for paired, we are ready. So we ran two systems, and on the first benchmark, we got 5.4 and 19.1. On the second, we got 16.6 and 3.5, and so on and so forth. So 1, 2, 3, 4, 5, 6 benchmarks. So the differences are, clearly you just subtract 5.4 minus 19.1, you get minus 13.7. And similarly the difference here, so you get 6 differences. So you do the sample mean, sample variance, sample standard deviation, and since there are only 6 samples, you have to use t-distribution. And therefore t-distribution, and then you use that t-value, and then square s is basically divided by square root of n is 6. So we do that, and the t-value for 95 is 2.015. So the 90% confidence interval is minus 7 to plus 7. So our answer is that the systems are not different because it includes the 0. So this is very straightforward. If you have paired observations, all you have to do is to take the difference and then you see the unpaired is little bit complicated. So I don't know whether we need to go through the theory here, but for unpaired you could have different number of observations. And so for the first one, you will have a sample mean based upon the number of observations. For the second one, you will have the sample mean based upon the number of observations. For the first one, you will have a sample standard deviation, and you will have standard deviation for the second one. So you will have 4 numbers so far. In spite of all these big expressions here, this is basically a simple formula for standard deviation, right? After you compute x bar and x bar A and x bar B, you compute the difference, and you compute the standard deviation of the mean difference. That has this little bit complication here, because what we are doing is we are subtracting 2 random samples. And again, if we were to tell you about what happens, and we are assuming here normal distributions. So if we take some numbers which are normally distributed and you take some other numbers which are normally distributed, you subtract them, the variance actually is related by this formula, and some of you who are sophisticated enough can figure it out, that the variance of that difference is this, or standard deviation of the difference is this. And the number of degrees of freedom is even more complicated. But basically, the degree of freedom has this formula. Okay? And so if you can calculate both S and nu, then you can use the T formula as before to compute the confidence interval. However, having said this, while you will do it, this kind of stuff for this particular chapter, but in future, I will tell you, you don't have to do it. That's why I'm not deriving all of this, because this is the part that you really don't use that much. So I'll tell you what you use in a minute. But if you were to do it strictly by the books, as they say, you will have to compute the standard deviation, you will have to compute the degrees of freedom, and then use those in the T value. So please make a correction on this slide. NA minus 1, NB minus 1. Now, what he was talking about is errata. How many of you have seen the errata? 1, 2, 3. Okay. All right. So there exists an errata for the book. It's on my website. If you go to my website, click under books, click under this book, then you will find errata, which is 13 pages long. So there are lots of things that have been corrected over the period. Please download that, print it out, and then correct your book, or somehow remember that there is a change. Okay? And so he brought up this issue that we know that this formula, when originally printed in the book, was wrong, and some editions of the book have been corrected. So that's the problem. 13 pages long is from the beginning of the book, but after that we had 20 printings. So each printing is more correct. But so the thing is, some of these might be correct for your particular printing, and some of these might not be. But you should know the existence of the errata. So this is NA minus 1 and NB minus 1. And so we do, and thank you for bringing that up. So now we do this now. So now this is the same data as before, but these 6 numbers are not paired with these 6 numbers. Now we don't know which workload is this and which workload is that. They could be very different. This could be the 5th workload, this could be the 2nd workload, and so on and so forth. So these are unpaired observations. Some 6 random workloads were run on system A, and 6 random workloads were run on system B. So these are unpaired observations. So we do mean, standard deviation for the first, and we do mean, standard deviation for the second. We do the difference of the mean, we do the standard deviation of the mean difference. This 3.698 came from that big formula. Well, it's not that big, from this formula. Degrees of freedom came from this big formula. So degrees of freedom comes out 11.921, which is actually not that different. Actually, I could have just used number 12 there, because we had 6 observations. But anyway, 11.921. And so 11.921, because that degrees of freedom is not listed anywhere, so we take it 12 anyway. So we go to the table with 12 degrees of freedom and 0.95, and we find 1.71, and therefore we find the confidence interval for the mean. And now after reading this confidence interval, we notice that the signs are different, and therefore the confidence interval includes 0, and therefore the two systems are not different. So generally, that example is not a good example, but when you do surveys, you don't ask the same person 2 questions. You ask 5 people here and 5 people there, and then you say, well, okay, so you are for the Democratic Party, what do you think, who will be the nominee? Then if you are the Republican Party, who will be the nominee? These are different people. So these are different workloads, right? And there is no relationship between this person and that person, right? So that is the kind of thing happens. And so, yes, I mean, obviously you won't be running different benchmarks random and then saying, well, we ran 100 benchmarks here, we don't know what we ran. But it could be that you're comparing utilization or something, so you had 100 things run and you calculate the utilization of the today's date, whatever the date is, and then 100 utilization thereafter. So there could be some cases where comparing things which are not related. Yeah, no, so this is why I'm going to bring it up. See, the thing is, okay, so time after time, every day when I watch the news, I do this calculation. When I watch the news, they tell you that Obama won so many percentage and whatever the Romney so many percentage, and so this was like 42 and 48 and 52, right? 4% difference. And then they say that the standard error is 5%. What does that mean? That means they're not different, right? I haven't defined a standard error, so hold on to that thought. But basically, given that standard error, I can calculate the confidence interval. Given the confidence interval, I can say that this is really, they are making fuss about things that they don't know. And the reason they don't know is because they took such a small sample. And that's why the standard error is so large. See what I mean? So yes, if you want to find out if people are interested in ice cream or not, the question is, then you have to make a statement that I could be wrong by so much percentage on this. So given a small sample, you are wrong so much. If you are a larger sample, if they would have taken a sample of the whole United States, then they would have found out that one will win by 1%. 2% or one number, right? But they can't do that. So they just make a very small sample and make an observation which has no value, because right there they are saying that I have no data. People don't understand that, but we who are statisticians, we right away say, oh, come on, what are you saying here? So in very fine print, they put that standard error, which is actually related to confidence interval. So you have to add that and then figure out whether this is the difference is significant. So now I'm going to tell you another visual test which is even more powerful, and I find it very powerful. When I say powerful, means I use it all the time. And I don't need to have too much of mathematics done behind it, and that's the kind of thing I want to teach you. So here's the thing. Suppose you have two systems, A and B. Now you're reading a paper. In the paper, they show you the confidence interval, which some people do. They draw two graphs. They put the confidence. So if the confidence interval between the two are such that they don't overlap at all, so the highest of this is below the minimum of that. Our second possibility is that the confidence interval overlaps so much that the mean of one is in the interval of the other. Or they are so different that the confidence interval overlap, but the mean is not in the confidence interval. You get these three cases? All right, so what can we say? Now you could do hypothesis. There are lots of books on statistics that talk about hypothesis testing. So I want to test the hypothesis that A is different from B, and they give you all the formulas, which we can go ahead and do it. And actually we can use that, because these are non-paired observations, we could just use that new formula, get the degrees of freedom and go to t-value and all that. But we don't need to do that, because all visually when you look at this, I can tell you that basically you can be assured that A is better than B in this case. You can be assured that A is same as B in this case. This is the only case where you need to, you cannot be sure either way. In this case, you need to run that formula. And why it is powerful? Because when you are looking at the graph, reading a paper, right away you say, oh, they are not different. What they will do is, these guys who have plotted the graph, they don't understand this part. So they will still show you everything, and they will say, look, my curve goes above their curve. My curve is better than their curve. But they don't notice that the confidence intervals are overlapping. Even though the means are not, but the confidence intervals are overlapping so much that the mean of one is in the confidence interval of the other. If that is the case, then means the systems are not different. So now can you do this visual test? Do you feel comfortable that if I show you two confidence intervals, then you have to check. What you have to check? You have to check whether they overlap or not. If they don't overlap, decision is done. If they overlap, how much they overlap? If they overlap so much that the mean of one is in the confidence interval of the other, decision is done. If they overlap little, then you need more. So here is an example. We take the same numbers as we had before, and so we come out with the confidence interval for the mean of A, confidence interval for the mean of B, and now we look at these two numbers. So the lowest here is 0.18 and lowest is 0.24. So the mean of this, mean of B is, where is the mean of B? 5.64 is in here, right? And the mean of A, 5.31, is in here. So this is that middle case, that the systems are not different. Now the next question is, should be used 90% or 95% or 99%. And I have said it so many times that by now you know the answer, right? So the answer is, it depends, because it depends upon the loss that you will have if you are wrong. How many of you have bought a lottery ticket ever in your life? Anybody? Okay, all right. What was the confidence that you had that you will win it? I mean, chances of your being wrong is what? So suppose 38 million people bought the lottery and you are one of them. Or let's keep it round number. Let's say 100 million people bought the lottery and you are one of them. Chances of winning, you know, without too much work, that you know 1 in 100 million. So you are going to be wrong, you know, I don't know, 9, you put 9,999,999 times. That is how much you are wrong. Right? Your right being is, you put 7 zeros and then you put a 1, 10 raised to minus 8. That is your probability of being right. So at that confidence you made a decision, right, and you felt good, is because that you will be 99.999% wrong. So that's why, the reason is because the loss is so little, $1 means nothing. Right? And the gain is so much. So if you just by chance were right, then you're all done, you don't have to work tomorrow. Right? All your life. So the thing is, the gain is so high and the loss is so little that you would rather be wrong than be right. You know? Of course you want to be right, but you can take chances to be wrong. On the other hand, just change those numbers. You are building a bridge, or building an airliner like 787, and the battery burns up. Have you heard this story? Right? And the battery burns up. How many billions of dollars are you going to lose? Company is going to shut down. How much right you want to be and how much wrong you want to be. You want to be 9,99999, write down 7 times. That is how much you want to be right. Even though we are going to teach you all this different 90% all the time, but don't use 90% all the time. It depends upon how much you are going to win and how much you are going to lose, and how much risk you can take. And so for some people $1 is a lot of value. For them that lottery ticket is very expensive. For some people it is nothing, right? And so they might even they might not even buy lottery, but basically I'm just saying, so that is the thing, okay? So the confidence level, 90% you don't have to have. You could have 0.0001% confidence, and that's good enough in many cases. All right? Now, having said all this, we might just use 90% all the time, but that is just because we are teaching a course. When we go to the real world, we have to be careful about what confidence we use, because if you use 90% for plain design, your company will be out of business pretty soon. On the other hand, if you use 90% for buying a lottery ticket, now here is another example. Suppose you want to be 99% sure. Let's say 90% sure that you build the lottery. How many tickets you have to buy? 100 million people, you have to buy 90 million tickets. Right? Would you really gain anything out of that? No, because they don't give you 100 million back. Out of 100 million, they give 50 million, and they give you 50 million. Right? So for $90 million, you are sure, 90% sure that you will get $50 million. So that's not a good distance. That's the kind of thing is that now, so basically, how much you're going to go and lose and how much you're going to win, how much you're going to gain determines how much confidence you want. The next topic is hypothesis testing versus confidence intervals. So most of the books on statistics kind of emphasize hypothesis testing. And in my view, actually, that is a little bit too statistical. And we want to keep life simple, and they are same. You get the same answer whether you go this side or that side, and therefore I emphasize confidence intervals throughout from now on. But it is same as doing hypothesis testing. So if somebody did the hypothesis testing, whether what is the probability of whether this is correct and that correct, you will get the same answer. So from now on, basically this is what we are going to do, confidence interval, and they're very powerful because they can be understood by anybody. Actually, people who don't understand confidence, for example, you didn't know probably before today that you could compare the confidence intervals like that, but people understand at least that, okay, this is variance. You can explain to your manager, you can explain it to anybody, and they will understand very fast. Now we go to the one-sided. So in some cases, you don't want to take 5% chance on this side and 5% error on the other side. Some cases the other error on the other side doesn't matter, and the error on one side is the only thing you care about. In that case, you have the confidence intervals, which are called one-sided confidence intervals. So for example, if you want the lower side, then you put all alpha on the lower side. So instead of alpha by 2, you have alpha. So when you want 90% one-sided, you put 0.9, not 0.95. And so you don't divide by 2. And similarly, if you want the upper side, then you put plus, and then you leave it there. And here is another thing too. I might use T all the time, because if you have more than 30 observations, T is same as Z, which means that whether you look at the T table or Z table for 31 observations and 32 observations, the difference is very little. Okay? So T becomes Z when you have more than 30 observations. So if you have a small number of observations, you use this, but if you have more than 30 observations, then that is Z. It's unit normal. So only for small numbers they are different. For larger numbers, the T and G distributions are same. Alright, so let's see this. Time between crashes. We had 972 observations. The mean time between crashes was 124, and the standard deviation was 198 on the system B, 153 observations. So here is an example of a workload which is different. And so, you are asking, can you do different workloads? So here it is the example. So this is the crashes. System A crashes 972 times. System B crashed 153 times. And we want to compare the systems anyway on the reliability case, right? So there is no relationship between these two crashes, and there is no relationship between any of the crashes with any other crashes, right? So we have unpaired observation. All right, so we do X bar and the difference, we do the S, and we do degrees of freedom. Since it is more than 30, we can use Z, and we use the Z, and the confidence interval includes 0, and therefore the systems are not different. The main thing new here is that we used one-sided confidence interval. So we don't have 17.37 minus here and the plus there, because we don't really care if the number is smaller.